It's the ultimate impossible question. What exactly happens when we push temperatures so high that our equations start spitting out infinities, our physical laws crumble, and the universe essentially puts up a giant mathematical do not enter sign? Today, we are journeying to the absolute ceiling of thermodynamics.
And here it is, 1.416 times 10 to the 32nd power Kelvin. Or, to put it another way, roughly 142 nonillion degrees. This is known as the Planck temperature. Now, this isn't just an arbitrarily massive number we calculated for fun. This specific value represents the hard, mathematical wall of our universe. It's the absolute maximum thermal limit before everything we know about reality breaks down completely.
Section 1. Hot versus hotter. Let's get some perspective.
To truly appreciate a number that massive, we really need to build a sense of scale. We're going to escalate from the familiar warmth of our everyday world all the way up to the most extreme furnaces of the cosmos. Starting on the left, a comfortable room temperature right here on Earth is around 300 Kelvin. Okay, jump up to the core of our sun and we hit about 15 million Kelvin. That's enough heat to fuse hydrogen into helium and power our entire solar system. But let's go hotter. When a massive star dies in a violent supernova explosion, temperatures momentarily spike to 100 billion Kelvin. That is a 1 followed by 11 zeros. Yet, as violently hot as a supernova is, it doesn't even come close to the Planck temperature. I mean, it's not even in the same neighborhood.
The crucial point here is understanding what actually happens to matter as we keep pumping up the heat. Around 1.7 trillion Kelvin, ordinary hadronic matter, like the protons and neutrons making up your body, literally boils. They just dissolve into this chaotic phase called a quark-gluon plasma, which is known as the Hagedorn limit for ordinary matter. If we keep going to an astonishing 10 to the 30th Kelvin, string theory suggests we hit another limit where matter transitions into a sea of fundamental strings. But finally, at the absolute maximum of our scale, we hit the Planck limit, the ultimate barrier.
Okay, let's dive into this. Section 2, the Planck temperature explained. So where did this ultimate limit actually come from? To answer that, we have to travel back to the late 19th century and meet the brilliant physicist Max Planck. Now, he wasn't necessarily trying to find the end of the universe. He was just searching for a universal language, a natural system of measurement that wasn't based on arbitrary human things like the length of a king's foot, but on the fundamental, unchanging constants of the cosmos itself. At the time, Planck was wrestling with this massive problem regarding black-body radiation. Older theories predicted that heating an object should release infinite amounts of ultraviolet light, an absolute absurdity known as the ultraviolet catastrophe. Planck elegantly bridged the gap by proposing something totally revolutionary. Energy is not a continuous wave. It's actually exchanged in tiny, discrete, finite packets, which he called quanta. And just like that, this single insight birthed quantum mechanics. By isolating the exact size of those energy packets, which we now call Planck's constant, he found he could combine it with three other fundamental properties of the universe. We have the speed of light governing relativity, the gravitational constant dictating gravity, the reduced Planck constant ruling the quantum realm, and the Boltzmann constant bridging energy and temperature. By bringing all these together, Planck derived a set of natural units. The Planck temperature emerges from combining these four foundational constants, making it the ultimate intersection of thermodynamics, relativity, and quantum mechanics.
This analogy simplifies all of that complex math perfectly. It's the universe's speed limit, but for heat. Just as Albert Einstein proved that absolutely nothing in the universe can travel faster than the speed of light, the mathematics of the universe dictate that nothing can ever get hotter than the Planck temperature. It is a hard physical ceiling.
Section 3. Why does physics break? So, what does it actually mean to hit that ceiling? Why can't we just add a little bit more energy and push the thermometer 1 degree higher? Why does physics simply break? Well, it breaks because our two most successful, brilliant frameworks for understanding the universe fundamentally despise each other at this extreme scale. On one side, we have Einstein's general relativity. It describes the macroscopic world of gravity perfectly, treating space and time as a smooth, continuous, predictable fabric. But on the other side, we have quantum mechanics, which tells us that at the microscopic level, energy and matter are chunky, discrete, and governed by strict rules of uncertainty. Normally, these two operate at completely different scales, so they never interfere. But at the extreme energy of the Planck temperature, you're literally forcing the incredibly massive and the incredibly tiny to overlap. When you combine their equations here, they don't give you answers, they just spit out impossible infinities.
The results of this mathematical breakdown is a physical environment described as quantum foam.
At the Planck temperature, the energy fluctuations are so incredibly violent and densely packed that traditional notions of here and there or before and after completely lose all meaning. Space and time cease to be smooth. The universe at this scale is churning, bubbling, and rapidly giving birth to spontaneous virtual black holes that just snap in and out of existence.
And this brilliantly illustrates our next point. Section 4, quantum foam and black holes.
Let's delve into what's actually happening with these tiny black holes in the quantum foam, because this shows us exactly why the Planck temperature is an absolute maximum. Imagine this discrete, dimensional network underlying spacetime. If you try to heat this system up further, you're pumping more energy into it, right? But because you're at the Planck scale, the gravity associated with that new energy is so unimaginably intense that it instantly collapses into a microscopic black hole. It doesn't raise the temperature. In fact, due to a phenomenon called Hawking radiation, these tiny black holes immediately evaporate, completely scrambling and destroying the very information you were trying to add. So any attempt to add more heat energy just creates larger black holes that radiate at lower temperatures. You literally, physically cannot go higher.
Now, you might be thinking this is all just purely abstract math, but it's really not. The universe has actually experienced this. If we rewind the clock all the way back, past the supernovas, past the formation of the very first stars, we arrive at the Big Bang. During the Planck epoch, which is the first 10 to the power of negative 43 seconds of existence, the entire observable universe was crammed into a volume smaller than a single proton, and it was trapped precisely at the Planck temperature. It was only by expanding and cooling past this exact limit that the fundamental forces could separate, and time and space as we know them could even begin.
Section 5. Beyond the ultimate limit.
We've scaled the thermometer to its absolute peak, venturing all the way back to the very first fraction of a second of the cosmos. So, what lies beyond the ultimate limit? Well, the most honest answer modern science can give us right now is we don't know what's beyond. But please do not see this as a failure of science. It's actually the exact opposite. This mathematical wall is the most thrilling frontier in all of modern physics. It tells us our understanding is incomplete, and this is exactly where human curiosity matters the absolute most. Physicists are actively trying to peer past this limit by rewriting the rules of quantum gravity into a unified theory of everything. And our best ongoing attempts offer some seriously mind-bending possibilities. String theory, for instance, introduces a concept called T-duality. It suggests that if you try to shrink a system past the Planck limit to raise its energy, it doesn't compress to an infinite singularity. It actually bounces and acts mathematically identical to a larger, expanding dimension. Wild, right? Meanwhile, loop quantum gravity suggests that space itself isn't a smooth background at all, but is made of discrete, countable chunks and nodes, meaning you literally can't zoom in any further than the Planck scale.
Both of these theories offer a tantalizing glimpse into a reality where our current rules of heat, space, and time are just the tip of the iceberg. Which brings me to the end of our explainer today and to a question I want to leave you with. Based on everything we've looked at, from the mathematical wall of quantum foam to the absolute mysteries of the Big Bang, do you think a temperature beyond the Planck limit is even physically possible in some hidden layer of reality, or is it truly the hard ceiling of existence? Let that bounce around your mind for a bit. We'll be diving into absolute zero, Planck time, and quantum gravity in future explainers, so there's plenty more to explore. Thank you so much for learning with me today, and as always, stay relentlessly curious.